You might have an idea about what imaginary numbers are now, and having a look at complex numbers in terms of the solutions to equations. You might have noticed that for some equations you have imaginary part, which means there's a complex root. And also you might have noticed that they come in pairs. So this is called the complex conjugate roots theorem. If you've looked at de Moivre's theorem and looked at roots of unity as well, you will notice that the roots come in pairs when they have an imaginary part. If you've been looking at the factor theorem and solving equations this way, you'll notice that sometimes there are imaginary solutions, but how would you know what the other imaginary solution is? So the other imaginary solution is always the conjugate. So we're going to have a look at this idea. So if x equals a plus bi, so this is a complex number, is a solution to an equation, then x equals a minus bi is also a solution to the equation, okay? So simply just noting that this is the conjugate of the first solution. Alright, so let's have a look at how that works. But before we do that, just a quick reminder about the fundamental theorem of algebra. Okay, so Gauss, it says here, did some work with equations, and this is a very important idea that whatever the power of the polynomial is, that's how many roots or how many solutions you expect to have to that equation. So if it was a cubic function you're looking at, that means you expect to have 3 solutions. Okay, so when you're solving an equation, we always make it so that the one side is equal to 0. Now for that cubic equation, you're definitely going to have complex, well not definitely, but you may have complex solutions, and if that is the case, then you can find out what the other one is easily by using the complex conjugate roots theorem. Now in your textbook, and by the way this is chapter 5 of book 2, it doesn't quote or doesn't state the complex conjugate roots theorem, but they do have it written here as the second last dot point. If p plus qy, where q cannot equal 0, so that means it must be a complex root, is a 0. So remember, a 0 means a value that fits into the function that makes the value 0. Okay, so if that's a 0 of a real polynomial, then its complex conjugate p minus qy is also a 0. Why do they bold the word real? It means you're only solving polynomials where the coefficients are real. Okay, so if the coefficients were complex or have an imaginary part, this theorem doesn't work. We're going to go through a couple of examples in a moment just to highlight this. What's also important to note that is every real polynomial of odd degree will have at least one real 0. Okay, so that means cubic equations always have to have one real solution. The other two could be real, or they could be both complex. And complex conjugates, by the way. You can't have the other two, one imaginary and one real. It doesn't work like that. Okay, so this example here, you can quickly see they say that negative 3 plus I is a 0. So that means you immediately can just say negative 3 minus I is another 0. Alright? So knowing that, then they can continue on with this question. We won't look at this one, but that's just the idea of how it works. Okay, so let's have a quick look at, say, question 6 here. says 2 plus I is a root of this fourth power or quartic equation. Can you find A and B? Alright, so give you a moment just to jot that down while I do the same. This is exercise 5H, question 6. X to the 4 plus ax cubed plus 8x squared plus 3ax plus b equals 0, and we know 2 plus I is a root. Okay. So firstly, we know that x equals 2 plus I is a solution. And we'll just write this down properly in a sentence form. That means we know the conjugate 2 minus I is also a solution. Now, because this is quartic, I'm missing 2 solutions. I don't know what the other 2 are. So we're going to factorize these solutions. We're going to write it with the brackets form, is what I'm trying to say here. So I know that there will be 4 brackets equal to 0. So we're going to write x minus each of these solutions. So x minus 2 minus I, that's for the first one. Second one will be x minus 2 plus I, okay, because I'm subtracting a negative. I don't know what the other 2 are going to be. Okay, so it'll be x minus don't know, x minus don't know. Now what we can do is we can expand and then equate the coefficients with the original polynomial. Alright, so first up, let's expand these. If you wrote this like in this way, you probably can utilize the difference of squares. Sorry, I wrote it the wrong way. If I write it like this, x minus 2 minus I, and then x minus 2 plus I. So you can see that's the real part and that's the imaginary part. So when I expand that, I've got x minus 2 all squared and then minus I squared, which is just plus 1. Okay, so that's what that first 2 brackets are going to look like. And then I can expand that even further. That will turn into x squared minus 4x plus 4 plus 1. So this is x squared minus 4x plus 5. Okay, so those 2 just turn into this quadratic expression. And then I'm going to have another quadratic expression, which I don't know what it factorizes down to. So now my equation turns into x squared minus 4x plus 5, and then some unknown quadratic equals 0, right? So remind you what the process of doing equations are. Having a 0 on the right hand side, and we're trying to factorize so we can slowly work out the solutions one at a time. I mean, we already have 2. We just got to work out what the other 2 are. Equating coefficients. So we can use our process of deduction. We know our quadratic must have a leading term of x squared. So I'm just going to continue writing my working up here. X squared minus 4x plus 5. Okay. Why do I know it's x squared? Because the leading term is x to the 4. So x squared times x squared must equal x to the 4. I can also write something about the last term. Oh, this is an interesting one. So the last term, the constant has to equal b. And we've already got a value here, which is 5. So normally what I would do is I would put plus an unknown quadratic amount here. I'm just going to use a color. I've run out of letters. They've already used A and B. I'll just double check the question is written correctly. Yes. Okay. So I'll just call this one k. Okay, so that's the x term, and then the constant there will have to be 5 over b. Sorry, not 5 over b. It will have to be b over 5. All right. I'll show you why that is. All right. So when I expand the two constant terms, 5 times b over 5, that needs to equal b, which is the constant term shown there. I've already checked the leading terms. Okay, so that's correct. Now I'm going to look at some other terms to expand. So the unknown coefficients given to me are here in the cubic one and the x term. I'm going to use the one that's known first. I'm going to do the x squared first. Okay, so I'm going to compare the x squared terms. Hopefully that'll give me one of the values, maybe not. Let's just see. To get x squared, I'll need this squared term and the constant. Alright, so I'm going to get x squared times b on 5. Now I don't care about the x squared, I just need the coefficients. So I'm going to get b on 5. That's one way to do it. There's another one. It's when you multiply the negative 4x and this kx. So I'm going to get negative 4k. And is there one more? Yes, there is. There's another squared one if I multiply the 5 and the x squared. So plus 5. Okay, so what I've done is I've just looked at the x squared terms here in the factorized form. And then if I look at the question I've been asked, they've already told me that value must equal 8. Okay, so if I just fix up this equation, I'm getting b over 5 minus 4k equals 3. Let's multiply everything by 5 just to have nice numbers. Just wondering whether that's needed. Maybe we'll leave it at this point. Oh no, we'll do it so that we can get a single b on its own. So we'll get b minus 20k equals 15. Okay, so I want to call this equation 1. Now let's compare some other terms, and this is expected, right? You're going to have some equations you need to solve simultaneously. Comparing the x terms. Okay, so the x term here is 3a. How do I get x over here? Can't use the squared term, so let's use the single x term. So the single x term can multiply with the constant here. So I've got negative 4 times b on 5. I've got negative 4b on 5. Alright, I can also do this 5 and the k. So I'm going to put plus 5. Okay, remember I'm looking at the x terms, okay? I think that's it. Can't have any other combination. And then that should equal 3a. So this is probably the worst one out of the two equations. Let's multiply everything by 5. So we'll get negative 4b plus 25k equals 15a. Okay. And then let's compare the cube terms. So it looks like we actually had to compare all of them to get this out. Then cube term, I can have a squared and a single, so I'm just going to get k as my coefficient. And also the same on this side, so negative 4. I think there's no other ones for cube. And then the cube term over here equals a. That's equation 3. So I've got 3 unknowns, a, b, and k, and then I've got to solve them simultaneously. So let's think about how we're going to approach this. This is the most complicated one, equation 2. 1 and 3 both have k in them, so what you can do is substitute 1 and 3 into the b and a to get this whole thing in terms of k. Alright, so I'm putting equation 1 and 3 into equation 2. So I'm going to get negative 4, and b is equal to 15 plus 20k. And then I'm going to put plus 25k equals 15. A is equal k minus 4. Success. Okay, so now you can solve for k. Negative 60 minus 80k plus 25k equals 15k minus 60. Okay, the 60s cancel. This is a strange situation. What this tells me, because I've got k on both sides, k must be 0. Yeah, so let's have a look at that just to make sure that makes sense. Yeah, it is possible to have k equals 0. Let's go with this. So k equals 0. We actually don't need a middle term. Interesting. So now I can find a and b. So from 1, you'll get that b equals 15. And then from equation 3, you'll get a equals negative 4. Let's write our solution now. So we're getting the factorized process, okay? So here, my equation has now become x squared minus 4x plus 5. Second bracket will be x squared, no k, so plus b, which is 15, plus 3, okay, equals 0. However, the question was asking to figure out a and b, so I've already solved the problem altogether, and it's already shown there. But as an extension, if I wanted to go further, I wanted to find the solutions, so I was trying to use this question as an example to explain the solutions. We've got complex conjugate roots here, and this is probably going to be complex conjugate as well. So if you think about it, x squared plus 3 is going to be factorized to x minus 3i and x plus 3i. Okay, so overall, the solutions are x equals 2 plus i, x equals 2 minus i, x equals 3i, and x equals negative 3i. Alright, because of the fact that I wrote 3i, which is a complex number, so that means the conjugate should also be the solution as well. So overall, this is just an example of remembering that if you have a solution to an equation that's a complex number, then the conjugate must also be the solution.